You ever stop and think about how our tech is so precise? How a computer delivers perfectly stable power, or how a car's suspension gives you that smooth ride? Well, it's not magic, not at all. It's really just a story about controlling energy. And today, we're going to pull back the curtain on the secret behind it all, the RLC circuit. Okay, I know what you're thinking. A swing set and a smartphone. What could they possibly have in common? It sounds totally random, right? But here's the thing. The answer unlocks this beautiful, universal rule of physics that runs both of them. So stick with me here, because you're about to see how a simple swing holds the key to taming electricity. All right, so to really get a handle on control, we've got to start by imagining a world with no control at all. So picture this, a perfect swing. I mean, perfect. It's in a total vacuum, so there's no air. The chains have zero friction. You give it just one little push, and what happens? It just goes. Back and forth, forever, never losing an inch of height. Just this endless, perfect oscillation.
And believe it or not, that idea of perpetual motion, it maps perfectly onto the world of electronics. You take a super simple circuit, one with just an inductor, that's the L, and a capacitor, the C, and, well, you get the exact same thing. The capacitor stores up energy, kind of like the swing at its highest point, and then it dumps it into the inductor, which acts like the swing's forward momentum. They just pass that energy back and forth endlessly.
Now, this perfect, non-stop oscillation, it actually has a technical name. We call it an undamped response. It's just pure, raw energy zipping back and forth with absolutely nothing to get in its way. And while that's, kind of cool in theory, in the real world, uncontrolled energy is usually a recipe for disaster. We need a way to rein it in. We need to tame it.
So, the big question is, how do you stop something that's designed to be unstoppable? Well, you introduce a tamer. And in the real world, this actually happens all the time without us even trying.
Think about a real swing at the park. You've got air resistance pushing against you. You've got friction in those squeaky chains. All of that stuff slowly sucks the energy out of the system until eventually the swing grinds to a halt. So to get that same effect in our circuit, we need to add something on purpose. We need to add our own version of electrical friction. And that's where the resistor comes in.
The resistor's entire job, its whole purpose in life, is to push back against the flow of electricity. It basically turns that electrical energy into a little bit of heat and gets it out of the circuit. And this whole process, this act of deliberately killing the oscillation, that's what engineers call damping. The resistor, that's our tamer. That's how we get control. Okay, and this is where things get really, really cool. Because depending on how much friction we add with that resistor, we can make our circuit behave in 3 totally different ways. I like to think of them as 3 unique personalities for how the circuit decides to settle down. First up, we've got personality number 1, underdamped. You can just think of this one as the bouncy response. This is what happens when we add a little bit of friction, but not too much. The underdamped response is exactly like trying to stop that swing with just a gentle push towards the middle. It doesn't just stop dead, right? No way. It swings right past the center, then swings back the other way, overshooting again, but a little less this time. It kind of bounces back and forth around that center point before it finally settles down.
All right, next up is the polar opposite. Personality number 2, overdamped. And as you can probably guess, this is what happens when we crank up the friction, like a lot.
We call this the sluggish response. The best way to picture this is to imagine trying to stop that swing by pushing it through a giant pool of molasses or thick honey. There's no bouncing, no overshooting, not at all. It just slowly creeps back to its resting point. Sure, it's stable, but man, is it slow. So we've got 2 bouncy and 2 slow. There's got to be something in the middle, right? The just right? And there is. That brings us to our third and final personality, the one that engineers are often chasing after. Critically damped. This is the Goldilocks response. This is it, the perfect balance. A critically damped system gets back to zero, back to stable, in the absolute fastest time possible, but without overshooting even a tiny bit. It's the perfect stop. It's like the swing just glides smoothly back to the center as fast as it can, no wasted motion, no bouncing, no sluggishness. It's pure efficiency. It's precision. So how do engineers actually dial in these different personalities? Is it just trial and error? Nope, not at all. It's all controlled by a surprisingly simple bit of math. It's like a secret code that tells the circuit exactly how to behave. All right, part 1 of our code is a value called alpha. That's the damping factor. You can just think of it as a number that stands for how much friction our resistor is bringing to the party.
More resistance means a bigger alpha. Simple as that. And the second part of the code, that's omega. This is the natural frequency. This number represents the circuit's natural tendency to swing back and forth, which all comes down to the inductor and capacitor. Basically, it's how fast the circuit wants to oscillate if we didn't add any friction at all. So here's the secret sauce. The circuit's entire personality just comes down to a battle between these two numbers. It's a fight between alpha squared and omega squared. If the circuit's natural swinginess, omega, is stronger than the friction, alpha, then you get an underdamped, bouncy response. If the friction is stronger, you get an overdamped, sluggish response. And what if they're perfectly matched? That's when you hit the jackpot. You get that perfect, critically damped behavior. It really is that simple. Okay, so this is a fun little physics lesson, right? But why does any of this actually matter? Well, because this concept of damping is, and I'm not exaggerating, one of the most critical ideas in all of modern engineering. Let's talk about the tech you use every single day.
Take a look at this. This is a graph from a real-world circuit. You see that initial spike? It overshoots, just like our bouncy underdamped swing. But look how fast the damping that an engineer designed kicks in. It kills that oscillation and brings the signal to a stable, steady value in just a few thousandths of a second. That blend of speed and control is everything.
I mean, think about it. Your car's suspension system. When you hit a pothole, you want the car to absorb it and settle down immediately. That's critically damped. You definitely don't want it to keep bouncing down the highway for the next mile, right? That's underdamped. Or the power supply in your phone. It has to deliver a rock-solid, stable voltage, no bouncing around. Even those automatic doors at the grocery store, they need to close fast but not slam shut. All of that, that's engineers carefully controlling damping. You know, when you zoom out, you realize what we've been talking about today is so much bigger than just circuits. This is a fundamental pattern of nature. It's the story of how any system, anywhere, returns to balance after it's been disturbed. So let's just nail this down one last time. The key takeaway is those three personalities. Underdamped, that's bouncy, it overshoots. Overdamped, that's slow and sluggish. And critically damped, that's the just right sweet spot, the fastest, most efficient way to get back to being stable. If you remember that trio, you've got the core idea.
And here's the really wild part. Once this pattern clicks for you, you'll see it absolutely everywhere. You'll see it in how an ecosystem recovers after a forest fire. You'll see it in how your own body regulates its temperature. You'll even see it in things like the economy. It's in every complex piece of technology we've ever built. So the real question isn't about circuits anymore, it's for you. Now that you know the secret of control, where are